Greg Scott Callan. My algebraic mesh I came up with back in 1999, and I've been keeping it a secret mostly, not by choice. Uh, yeah, back in 2003, I emailed Brian Green, uh, Lisa Randall, and Frank Welsick about combining three physical laws into one equation. And after I sent that email out a few weeks later, Brian called me and said, "This equation of yours could be very embarrassing." So I asked him, "So it's wrong because it's embarrassing?" And he says, "It's embarrassing that nobody thought to try that." And I've been trying to get this out here. I'm I don't have a degree. I just like math, physics, computers, chemistry, and my education's a mess. I can't straighten it out. It's so bad. But yeah, if you take Einstein's energy equation, you multiply it by Newton's gravitation force, and divide it by Coulomb's electromotive force, you get all the possible parts of physics into one equation. You got mass, distance, time, and charge all in there. And so I believe that it describes, it's almost there. There's like something going on with the three-dimensional geometry of magnetism that isn't in here. But charge is, and maybe if charge is, we could figure out the rest of it. So, um, yeah. And of course, you could do it the other way around. Have the forces inverted with Coulomb in the numerator and Newton in the denominator. And so there's two quantum entangled particles, um, mass one and two, and charge one and two. The number one is the same object in both equations, and you can make it all. You can make each one of these the same object, so it would perceive the object would seem to behave according to its own entanglement. It'd be able to observe itself basically, and so yeah, the forces entangle each other when they interact with each other, and they're basically dark matter at that point. And when observed by Einstein's equation, the third mass, then it becomes real. Otherwise, it's invisible in the probability wave. So, yeah, I took all the constants in all three equations and combined them into one. Well, actually, two for two different equations. There's L2 and L1. That's L1 is gravitational constant times the speed of light squared over the electromotive constant, and that becomes L1. So you have L1 in the numerator, three masses multiplied by each other. They could be different or the same mass, doesn't matter. And then two charges. The two charges is kind of a bizarre thing. You'll notice that the charge mass ratio here, 3 and 2, corresponds with quarks in subatomic matter. Yeah, the the quarks, they have a plus or minus 1/3 and a plus or minus 2/3 charge on them, not a full electron's worth of charge or proton. So I think this explains quantum entanglement, quarks, um, quantum gravity. So the Fourier transform includes velocity, and you should know velocity is a distance over a time, distance vector if you're multiple dimensions, a distance vector over time. So if you take that v and you try to isolate it into one side of the equation, you get this mess. And then if you break velocity into distance vector over time, solve the equation for time, I'm proposing that this is the true nature of time here, right here. So look at this. So this factor right here, subtracted from 1, this factor right here, if you can make that equal 1, you get a 0 in the denominator, and time stretches out to infinity. Impossible to do, maybe, I don't know, but the numbers seem to work very, very easily. Nothing unusual. With no mass or charge or energy in this equation, unusual, you get the 0 in the denominator if it's 1, and then it blows up. So let's look at those numbers. If you calculate L1, you get this number, which is got the same mantissa almost to G, the gravitational constant. See, it's real close. And that's because K is a little less than 9, and C is a little less than 9, real close to 3, and this is real close to 9. And when you square C, it becomes 9 again, and 9 over 9 is going to give you 1. Going to give you 1 for a mantissa. So when you multiply by the gravity, you get the gravity equation. You get the gravity mantissa. You don't get the same exponent, though. This is a much more reasonable exponent, don't you think, than 9 or minus 11 or 8. So, it's a nice number for L1. L2, I used to do this equation only in L2 because I knew this one was more practical and it'd get more attention. People would start figuring it out and doing something malicious with it. If you can artificially make that equal to 1, you get 0 in the denominator, time becomes infinite. So, here we are, making that, here's the mass cubed, here's the charge squared, here's the energy. Look at that, 84 and 9. Those are nice, reasonable numbers. You get a 1. So here, at 90 kilograms, 9 volts, 6, even closer to the whole number, and it equals 1. Yeah, you take this number, multiply it by the cube of mass, divide it by the voltage squared. Yeah. So 90 kilograms, about 200 pounds. 9 volts, of course. You're looking at just a standard battery off the shelf. And 6 joules is about 4.4 foot-pounds or something like that. So if you have like a briefcase with you and you charge up your static electric voltage to 9 volts, and then you weigh about 200 pounds, what's going to happen? I don't know. Why this would work, I'm not sure. I haven't put it into practice yet. I've seen a lot of weird stuff happen when you try this, but I can't duplicate my results.